So should I ask now, or I can ask at the end of class also? Not a
Yeah,
problem.
maybe at the end of the class will be better. So
Right, sir.
go back
Right,
to
sir.
the notes and we can
Sure,
discuss.
sir. Sure.
So we talk about propagation of uncertainty. So we sort of got an introduction last class that when we have a uh, dependent quantity that we want to estimate, which is a function of many different independent quantities. And the independent quantities, each one of them, you actually measure. So each one of these quantities would be associated with some kind of uncertainty in the measurement. Now the question is how the uncertainties in each of these independent quantities can influence the uncertainty of the dependent quantity. Okay. So just to give you a very simple example, let's say you want to estimate the time that you require to completely fill a swimming pool, for example, using a garden hose. So one way is to, wait very long time and actually calculate the time, measure the time. But that is sometimes not the right approach. So instead, um, you take a small volume, let's say a bucket, and using the garden hose, you basically find out the time that you need to fill the bucket. And if you know the volume of the pool, and if you know the volume of the bucket, and the time that you took to fill the bucket, you can estimate how much time you require to fill the pool, right? If you estimate this way, then the volume of the pool, the volume of the bucket, the time required to fill the bucket becomes important, right? Any uncertainty in any of these quantities would influence the uncertainty in the target quantity, that is the time that you need to fill the pool. So basically how the measurement uncertainty of individual uh, secondary quantity, primary quantities would affect the uncertainty of the derived quantities. That is the um, thing that we learn in propagation of uncertainty. Okay. Let's say in general, if we have a dependent quantity y and it is a function of, let's say, x. So we have only one dependent quantity, one independent quantity. And for example, if you take a spring and you apply some force, you get some displacement. So F is k into x, right? This is this kind of example where y is a function of x. Now, let's say we measure x a number of times, okay, at some operating condition, so that we establish a sample mean and also uncertainty due to the random error of this mean value. Let's say you have measured x many times and you found this is the mean, and you also found the standard deviation, and from that you found the random uncertainty, which is p mu p 6 bar, right? This is the random uncertainty. Now the question is how this random uncertainty will influence the prediction of y, right? We can say that the true value of y would fall within a range. Let's say it may fall within a range of y mean plus minus of delta y. So this is the range within which the true mean of y, that is y prime, is expected to lie. And this is, of course, going to be, since y is a function of x, y mean plus minus delta y is going to be a function of x mean plus minus t nu p Sx mean. Okay. Now, if I expand the this in the Taylor series, okay, so I can write this as f x mean plus minus dy over dx at x equal to x mean into the subscript I am just neglecting, so t into Sx bar plus half into d square or dx square into t square plus so on. This is how you expand a function in Taylor series, right? You take the slope of the curve into the additional term, and you put the second order where you take the secondary derivative and the square of the term divided by 2 and so on. Now, if you neglect the higher order terms, anything higher than the first derivative, as you go higher on term, because this term is anyways is small. If you take square and cube and fourth order and so on, they will be very small quantity. So if you neglect the higher order terms, then, and this is basically your y mean. So you can write delta y is approximately equal to the slope of the curve dy over dx at x equal to x bar into tsx. Okay. So if I pictorially represent this, let's say I have x in the horizontal axis and y in the vertical axis. Let's say I have a curve which is this. Now, for a mean value of x bar, right? For example, you are measuring displacement and predicting force, and you take 10 measurement of displacement, you will have a mean, and corresponding to that mean value of displacement, if you know the stiffness, spring stiffness constant, you will have a corresponding value of y mean, right? But then your measurement can have random errors. So you can have on this side, you'll have x bar minus tsx bar. On this side, you'll have x bar plus t sx bar, right? So accordingly, your y will have plus minus delta y. So you will have y bar minus delta y, and we'll have y bar plus delta y, and this dy by dx is basically slope of this curve about this point, right? We said dy by dx at x equal to x mean at this point, at this very point. Okay. So this is basically your dy or dx at x equal to x mean. Okay. So what we see that a small random uncertainty in the measurement of x brings about an uncertainty in the value of the derived quantity, which is y. Okay. So this delta y is basically the uncertainty in y. Uy is basically dy over dx at x equal to x mean into, so this is basically the uncertainty in x, so this is ux uncertainty in X. Okay. So if you have an uncertainty in the independent variable, if you know the dependence of the dependent and independent variable, if you take the gradient of that and evaluate at the mean value of the independent parameter, you can estimate the uncertainty of the dependent parameter. Okay. Now this is something that we took as very simple relation where we have the dependent parameter y is a function of only one independent parameter. Okay, but there may be situation where y is a function of many different primary quantities. So it may be a function of x1, x2 up to xl. Let's say L different number of independent parameters. For example, if you want to measure the pressure drop across a tube, you have the formula which is the friction factor, length, square of velocity, now 2g into diameter. Now you see that how each one of these variables, length, velocity, diameter, affect the pressure drop, right? So how do we estimate in that case? That is the question. So let's say we have some kind of dependent variable, let's say R is a function of L different independent variable up to XL. Okay. So the best estimate of R, the true value of R is R prime, and our R prime is basically R min plus minus the uncertainty in R at some probability 3%. Okay. So where your R bar, like the previous case, it is now going to be a function of x1 bar, x2 bar, 3 bar, and so on. Right? The mean value of the dependent quantity is going to be a function of mean values of individual independent quantities, and the uncertainty UR is going to be a function of the individual uncertainties. Uncertainty is x1, uncertainty in x2, and so on, u xl. Okay, so this basically represents uncertainty in each of these variables. Like in the previous example I gave, it is a function of length of the tube, the diameter of the tube, the velocity inside the tube. So uncertainty in velocity, uncertainty in diameter, uncertainty in length can affect uncertainty of the pressure. Okay, so and from the results of the single variable that we talked about here, this we know that we can know that the uncertainty in the dependent variable would be related to the uncertainty in the independent variable through this gradient, right? So from here we can say that the uncertainty in R can come from dou R over dou xi at xi equal to xi bar into uxi. So this is, let's say we have ith independent variable, its contribution on the independent variable that is indicated by ur subscript I, which is the gradient of the dependent variable with respect to the independent variable evaluated at the mean value of that particular independent variable into the uncertainty of the particular independent variable. Okay, So now we have many such, right? We have I equal to 1, 2 up to L. Okay. So how do we find UR? Okay. So one such approach is called using root sum square approach. RSS stands for root sum square approach, where we say that UR, let's call this as, so here this term let's indicate by some theta subscript I. Okay, so basically URI will be equal to the slope, which is theta subscript I into UXI. Okay, so considering all these i's at 1 to L, you can say you can take a root sum square approach. That means you can write UR equal to I equal to 1 to L theta I UXI bar whole square, then square root. So you multiply theta I with UXI, square of that, and you do that for I equal to 1 to L, and then whatever you get, you take square root of that. So this is one approach where how you can find the uncertainty in the result, where the result depends on many different variables x equal to xi where I equal to 1 to L. Okay, so this is one approach. Yeah.
Sir, sorry, sir. Just can you please? I followed that UR, but what is it for URI actually?
So this says the effect of the ith independent variable on the dependent variable. See, URI will be the uncertainty in the dependent variable coming from the first independent variable, second independent variable, and so on, because we have L different independent variable, right? So effect of each one of these on the uncertainty is indicated as URI.
Okay, but will not be comes all together under the UR?
Yeah, altogether it has come here.
Okay, sir. Okay. Yeah.
You got my
Sure. Yeah.
point. Altogether
Thank
it
you.
has come here.
Yeah, thank you.
So this is one approach. The second approach, so I will talk about another approach and then I will take an example so it will be clear. So the second approach, so one of the limitation of this approach is that here you have to know the functional relationship of R and X. Okay, let's say you do not know the functional relationship, or you are not able to evaluate the gradient, then this method will not work. Okay, so you can use some numerical approach to estimate the propagation of uncertainty, that is known as sequential perturbation. Okay, so I will talk about the sequential perturbation method to evaluate the uncertainty propagation. Sequential perturbation method. Let's say your result is specified by some R naught. Okay, and R naught is a function of many different variables x2 up to xl. Now, each one of these will have some uncertainty associated, right? Ux2 and so on, and Uxl. Okay, so we can write R1 plus is f x1 plus ux1, x2, xl. So you can see that we are only perturbing the first variable. Okay. Why it is called sequential perturbation? Because one by one we will perturb the variable. Then I go R2 plus. R2 plus will be function of x1. Now x2 plus ux2. Okay. x3 up to xl. Now similarly I can write R3 plus, only x3 will be perturbed. So if I continue like this, I can write RL plus is function of x1, x2 up to xl plus uxl, right? So you can see that from this nominal function, I'm evaluating that function first, perturbing x1, considering the uncertainty, everything else remaining fixed. In R2 plus, I am only considering the uncertainty with x2. In RL plus, I am considering the uncertainty in xl. Similarly, I can find R1 minus is function of x1 minus ux1, everything else remaining the same. R2 minus is f x1, x2 minus ux2, xl. And if I continue like that, I can write RL minus is function of x1, x2, x3 up to xl minus uxl. Okay, so I have R1 plus and R1 minus, similarly up to RL plus, RL minus. Okay, now I define delta Ri plus is Ri plus minus R naught. So here, this is basically the nominal value of the dependent variable and nominal values of the independent variable. Now I have considered the uncertainty in the first variable and second and so on. Now in general, let's say here Ri plus will be f x1, x2 to xi plus uxi, right? So delta Ri plus is Ri plus minus R naught. Similarly, delta Ri minus is Ri minus minus R naught. So delta Ri I define as delta Ri plus minus delta Ri minus divided by 2. Now this will be equivalent to, if you remember in the previous case, this is basically the uncertainty in the ith variable. This will be equivalent to theta I uxi, right? So this will be equivalent to theta I ui in the previous case. Now in the previous case, how did we find the uncertainty in R? We said theta I ui square sum I equal to 1 to L half, right? This time we would take this as theta ui. So your uncertainty in your result U naught is going to be sum I equal to 1 to L delta Ri square half. Okay. So this is how you are going to find the uncertainty in the dependent variable using sequential perturbation method. Okay, so we have learned two different methods, but we take an example, okay, so that it will be clear to you how you are going to evaluate. Okay, so we take an example. Okay, so
Sir, sir,
yeah.
can you show me the last slide, sir? Just we have missed out the last.
Yes, yeah.
Professor, just one silly thought I had. This theta is basically that
The slope of the dependent variable with respect to the independent variable.
so del R upon x,
Del
del
R
xi.
over del x, del R over del x at x equal to x bar.
Okay, sir. Right, so right.
Del R over del xi at xi equal to xi bar. Okay, that is theta.
Right, sir.
Okay, sir. We noted. Sir.
Writing? Okay.
Thank you, sir. Finished.
Right. Okay. So we take an example. We say that for a displacement transducer, so the question is that for a displacement transducer having the calibration curve y equal to ke, estimate the uncertainty in the displacement y for E equal to 5.0 volt, 5.00 volt, if K equal to 10.10 millimeter per volt, with the uncertainty in K specified as plus minus 0.10 millimeter volt and uncertainty in the voltage as plus minus 0.01 volt at 95% confidence. So anyway, this is a material here. It can be any value of confidence. So it will just propagate. Okay, it will be the same in the data. So how do we approach this problem? Okay, so this is, you know, that in a displacement center transducer, you basically read the voltage output and there will be a calibration constant, and depending on the voltage output, you basically predict the displacement, right? So here the calibration constant has an uncertainty, the voltage measurement has some uncertainty, and you are trying to find how the uncertainty in the calibration constant and uncertainty in the voltage measurement propagate, and that gives you some uncertainty in the value of displacement measurement. Okay, that is the problem. So we are essentially saying that, like the case that we took in the example, so y bar is a function of E bar and K bar, and like we studied in theory, we say that the uncertainty in y is going to be a function of uncertainty in e and uncertainty in the k, right? And we also saw in theory that the uncertainty in the result, that is uncertainty in the y, will be theta I ui sum square and half. Here basically your I is 1 and 2, right? You have voltage and spring constant. So sorry, the calibration constant. So you have theta E ue square and theta k uk square. And we said that theta I is basically dou y over dou xi at xi x bar, right? So here theta E is basically dou y over dou E. Okay. So if we take so y equal to k into E, right? So dou y over dou E will be simply k. Okay. And similarly, if you want to find theta k, dou y over dou k, that is simply E. Okay. And so if you just substitute the values, so ui will be, so theta E is first theta E is your k, right? And k is it should be nominal k, right? It should be nominal value. So this is basically your nominal value of k is 10.10. So that is 10.10 into UE, uncertainty in E is plus minus 0.01, so 0.01 square plus theta k is the nominal value of E, which is 5.00 into the uncertainty in k is 0.10 square and whole thing square root. So if I just do the calculation, I can get this as 5.51 mm. Okay. So this is the uncertainty in the y. And what is the nominal value of y? Nominal value of y is k into E. K is 10.10. E is 5.00. So this is basically 50.50 millimeter. So basically the best estimate of y prime is 50.50 plus minus 0.51 mm. That is the best estimate of the y prime. Okay, so how the individual uncertainties have contributed to the total uncertainties, okay, using this formula. Is it clear, everybody? Okay. Then we would try to do this using the second method, that is the sequential perturbation method.
Sir,
Yeah.
to ask again. How dou y by dou e is equal to k and dou y by dou k is equal to e?
So it is basically your derivative of dy over dE, right? So if you take derivative of this, k is a constant, so dE over dE becomes 1. So you get k, right?
Okay, got it.
Okay, so we take sequential perturbation method. Sequential perturbation method. So here we said that we are going to find out these quantities. We make a table I and xi, ri plus, ri minus, delta ri plus, delta ri minus. From there we get delta ri, and we said that u of y is basically delta ri square sum I equal to 1 to L half, right? This is the formula. And we also said from theory that delta ri plus is ri plus minus r naught. Similarly, delta ri minus delta ri plus is delta ri plus minus r naught. Delta ri minus is ri minus r naught. Okay, and we said that delta ri is delta ri plus minus delta ri minus divided by 2. So this is from theory. We had all this. Okay. Now here so let's say we go I1 and 2, we have two variables. So the first variable is E, the second variable is K, right? Now, if you want to find Ri plus, okay, you want to find Ri plus. So the Ri plus, you have to, so Ri plus is basically the first variable is E, so you have to take 5.00. So there you have to bring in the perturbation. That means the corresponding uncertainty is UE is plus minus 0.01. So 0.01, right? That into the nominal value of K, which is 10.10. Okay, and this will give you 50.60. So Ri plus is 50.60. Similarly, Ri minus is 5.00 minus the uncertainty associated, that is 0.01, into 10.10. This will give you 50.40. Then you have to do the same for K. So this is for E. For K, Ri plus will be, you introduce the perturbation now in K. So 5.00 is the voltage into K is 10.10. There you introduce perturbation. So the uncertainty in K, UK is basically 0.10. So that if you find out, you get 51.00. So this is 51.00. Now similarly, Ri minus is 5.00 into 10.10 minus 0.10. That will be equal to 50.00. So once you have found these Ri plus, Ri minus for the first variable, second variable, then delta Ri plus is basically from here Ri plus minus R naught. So what is R naught here? R naught is basically the nominal value, that is E nominal into K nominal. So E is basically 5.00, K is 10.10. So the nominal value is 50.50. So delta Ri plus is 50.40, sorry, 50.60 minus 50.50. So that is 0.10. Similarly, delta Ri minus here is 50.50 minus 50.40 minus 50.50. That is minus 0.10. That is for E. For K, delta Ri plus is Ri plus, which is 51.00 minus 50.50, that is 0.50. Similarly, delta Ri minus is Ri minus, which is 50.00 minus 50.50, that is minus 0.50. Okay. Then we find delta Ri plus both, for both, right? E and K. Delta Ri is delta Ri plus minus of that divided by 2. So 0.10 minus of minus 0.10 divided by 2, that will give you 0.10. Similarly, for K, 0.50 minus of minus 0.50 divided by 2, that will give you 0.50. Okay.
Sir, sorry. Can you just explain the K for delta Ri plus
Which one,
in
sorry?
the numbers? For serial number K for K.
This one, huh? So delta Ri plus
Yes.
is basically Ri plus minus R naught. That is Ri plus is, we have already found, 51.00. R naught is minus 50.50. That is equal to 0.50. Okay. Similarly, delta Ri minus is 50.00 minus 50.50, that is minus 0.50. Okay. So once we have found all these, then we can find uncertainty U of R naught. I can find now is delta Ri square, right? 0.10 square plus 0.50 square. Sum them up and take square root. And that will give you your true value 50.50 plus minus 0.51 mm. And you can see that both the methods have yielded the same result, right? Whether you use the differential method, taking the slope, we got 50.50 plus minus 5.1. Using sequential perturbation method also, we got the same answer. Okay, both methods will yield comparable results. But when the data is very precise, there may be some slight difference that may arise. Otherwise, they should yield identical results. Okay, so I would stop here. But if you have question, we can discuss.
Sir, I had a doubt on one previous class.
Yeah, I would open that and maybe we can.
Yes, sir. So for a normal distribution curve.
Yeah. Just I'm opening so that you can. Just 1 second. Let me share that file with you. Yeah, I think this
yes, sir. So basically, we had derived that beta variable, sir, beta and z variable.
Because in this class or maybe the previous class?
Previous classes, sir. I think just after the like histogram plot, now we have derived that. No?
Okay, that was class to last class, not the last class. Okay, let me open that one as well. Okay, you can ask. I mean, I can.
So basically, sir, that px was actually 1 upon sigma root 2 pi and then x minus x bar square sigma square exponential 1/2, right, sir? That was the thing.
Yeah.
And the probability of x lying between x dash minus delta x and x dash plus delta x. That was integral of x dash minus delta x to x dash plus delta x px dx.
Yeah.
Right, sir? And then we define a variable beta where the beta was x minus x dash divided by sigma. And z1 basically x1 minus x bar divided by sigma, right, sir? And then we substituted the value of that beta into the main equation, and we got the equation like p z1 minus z1 to beta 2 z1 will be equal to 1 upon root pi minus z1 to z1 e to the power beta square by 2.
Yeah.
And d beta, right, sir?
Yeah.
So this is typically a this is typically done by the integration by substitution, if I'm not wrong, right, sir?
See, this is typically you have e to the power minus beta square by 2 d beta, so it will like e to the power minus x dx.
That I got, sir.
Yeah.
So basically, if I do d beta, I'll get dx divided by sigma, so that sigma will get cancelled out, and this whole term will be replaced by beta square by 2. That is right. But how this x minus delta x and x plus delta x is replaced by minus z1 and z1? That I was not able to.
So basically, your x prime plus delta x is basically beta into sigma plus x mean. Okay, so your x minus delta x will be sigma beta minus x prime. Okay, so basically when you integrate px dx, then you are basically changing variable from x to z, right? So your limits when you go to z1, okay, your x minus delta x is basically becoming as Z1. Okay. And
Okay.
your x plus x prime plus delta x is becoming plus Z1. Okay, so if you look at here, this will be clear. Like, I mean, there's a curve that I have drawn. Let me share this with you. Just one second. Give me a second. So, I think now you are able to see, right, this curve.
All right, sir.
Yeah, just one second.
No, just in this situation actually.
No, not this. Too many windows. Okay, so now you can see, right?
All right, sir.
Yeah, so what we meant was that, so you have x and you have px. So we are saying that the probability that a point would lie within this range, this is the best estimate, minus delta x to plus delta x within this range.
All right.
Now, when we went from x to beta or z, the difference between beta and z is that this is at a particular value of x, but beta is in general, right? You can make arbitrary value. That is the difference between beta and z.
Right, sir.
Now, if I change the variable from x to beta, okay, so I am saying that when x equal to x prime, your beta equal to 0, right? So
Right.
beta equal to 0 is here, right? And when x equal to x prime plus delta x, okay, your beta will become Z1, right? So it is basically x prime plus delta x divided by sigma. So that is basically becoming your Z1. Similarly, when you go x minus delta x, so when x becomes x prime minus delta x, so this will become minus delta x by sigma, which is signified as minus Z1. Okay. So x particular value minus x prime is basically delta x, right? So this value, whether it is plus delta x or minus delta x. Okay. So when it is plus delta x, it is Z1. When it is minus delta x, it is minus Z1. That's all.
Cool, sir. Got it.
Okay.
Got it. Thank you.
From where we can get it?
Okay. Any other question from today's class? Any earlier class? Okay, so if there are no question, I will stop here today. Tomorrow, I plan to talk about detection of outlier in a data set, and we will talk about Savonet's criterion that is typically used to identify outliers based on some statistical method, and then how to get rid of outliers and recalculate the statistical variables like mean and standard deviation. So
Professor, sorry, is it possible to share the notes, whatever, maybe if something is missed, you can just make it.
Yeah, see, this is the thing. We normally encourage that while I'm teaching, you take notes.
Yes.
But if you miss any classes, you can individually write to me. Or you missed, writing some portion of the thing,
yes.
Then I will, in that case, I will share with you. Okay. So in the earlier years also, we have been following this, and I mean, in a way, we are instructed to do that because we expect that when we are teaching on the board, you also write. And
we're writing with some words, some lines.
that is okay.
Okay, I will.
what I will do is, I mean, let's make it this thing. So let's say before the quiz, I can share the specific notes you would have missed, so I can do that. But
Thank you so much.
you can also get it from your friends and colleagues. But if you
Sure.
struggle, you write to me, I will share.
Yeah. Thank you, sir. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, all of you.
Thank you, professor.
Thank you, sir.
Sir, yes.